Hello, we are Team 8 from 477 and our project is Tensor Processing Unit TPU on FPGA.
Our Tensor Processing Unit is designed specifically for edge inferencing, delivering machine learning acceleration. It features a unified buffer with dual read and write port, memory banking, and innate data storage to maximize data bandwidth. It also has a specialized matrix multiplication unit for innate convolution acceleration, and a software stack for quantization and compilation. With a suite of hardware and software solutions, this TPU achieves faster computation while reducing power consumption and chip area, making it ideal for energy-efficient edge applications.
So here's our TPU design. We first plugged in the power jack to power on the PCB. And as you can see, the green LED lit up, and that's because we flashed a loopback test into the FPGA. And as you can see over here, when we type something on the keyboard, it's able to send it out and print it in the terminal through the USB UART. The user also has an option of modifying the TPU design. To do so, they would have to plug in the JTAG header, select the FPGA device to program, and they would have to upload the bit stream generated of the new TPU design. Once that's done, click OK and program the device. And now the FPGA is flashed with the new program.
In order to utilize our TPU, users must first obtain a quantized model. In our example here, we have created a small CNN that was trained on the MNIST dataset. Now that we've successfully trained our CNN, we can now move on to quantization. Using the PyTorch backend, we prepare, calibrate, and convert our CNN to a quantized CNN, converting the weights, biases, and intermediate activations from floating point 32 to int 8. This reduces the memory footprint and enables accelerated computation in hardware. We have an unquantized SqueezeNet model from the Torch Vision library and compared it against our own quantized version. As you can see, there was a reduction in size by 2 megabytes.
In order to prepare a quantized model to be sent to our TPU design, we created this Python support file to load in our model and print it all out into a binary file, which we will then send through UART. And you can see here, all of our weights are getting converted into binary. In addition to converting our quantized model to byte data to be sent over UART, we also need to encode some binary instructions to also be sent. Since all of the accelerated matrix convolution is happening inside the FPGA, it is invisible to the human eye, but what we can provide is a simulation of the exact same hardware on our FPGA with detailed waveforms of what is supposed to be happening. So you can see here in this section of code, we send data via UART, and then we go through a series of instruction fetch and executes to complete the convolution, and then we write it out to the host and go back to idle.
Currently, our hardware design is still being debugged. However, in a fully functional TPU, the user can launch a program by writing data to the USB COM port and wait for result to be passed back to the USB port. User can then post-process the return data accordingly. In this case, the MNIST-based model shows that the input image is a number 3.
And that's our Tensor Processing Unit, TPU, built to meet the needs of modern edge devices. Thank you.